Hey, how are you doing? This is Mike here again, and I'm going to continue on with some more interesting relationships between polar equations and Cartesian relationships. I just really I find this very enjoyable, and I really like seeing the relationships and how you can go from one to another. It's sort of like uh, I feel very excited when I finally understand language translation. So when I hear something, for example, in Spanish and I understand it in English, I get really excited. This to me is a very similar relationship between two different languages that ultimately mean the same thing. So just to continue on, I just like to talk about some reasons why we are going to use polar versus, well, not really reasons, but the reason why sometimes it's easier to graph polar versus Cartesian on the xy plane, Cartesians. So if we were to look at a a vertical line would have to be written in the form of r cosine theta, and this could equal to 2. Remember, r cosine theta is we said that x by definition is r cosine theta, y is r sine theta. These are in prior videos. R squared equals to x squared plus y squared, and we know tangent of theta is equal to y over x. So these we just, I put into memory. So if we know r cosine of theta equals to 2 and r cosine of theta equals to x, this is the same thing as me saying x equals to 2. And this is interesting because my TI graphing calculator doesn't know how to graph vertical lines. Well, it doesn't know that, doesn't know how to, but I find it really fascinating to me that I can use my polar form and graph some interesting outcomes. So I can graph some very interesting outcomes. So I'll show you that in a second. Let's say, for example, we wanted to look at r squared cosine theta times sine of theta equaling to 6. This is the same thing as me saying r cosine theta times r sine of theta equaling to 6. All I do is split up that r squared. And we know r cosine theta equals to x and r sine of theta equals to y. So this is the same thing as me saying x times y equals to 6. Or we could say that y equals to 6 over x. And those are going to graph the exact same way. So I'm just going to show you. So this one goes to this guy. These two are this guy. If we, this is something I pulled out of your textbook. If I look at x to the fourth plus y to the fourth, y to the fourth plus 2x squared y squared plus 2x cubed plus 2x cubed plus 2xy squared and minus y squared equaling to 0. And I were to ask you to graph this, I know most people would probably have heart failure looking at this and say, oh my goodness, that's just crazy. This converted to the polar form is equal to 1 minus cosine of theta. And 1 minus cosine of theta, as we're going to advance through these sections, is actually going to be very easily graphed. So I'm sure some of you are just on your seats right now about how to use the graphing calculator. So I'm going to use my graphing calculator here just to show you how I would graph 1 minus cosine of theta. So I'm just going to be pretty quick about this. So I have the old TI-83 model up here, but this works pretty consistently, I believe, for any other models. The first thing I look at is that I am in the form of the Cartesian plane, so I want to change this. So I'm going to go to mode, and I'm going to change from my functional analysis to my polar analysis. So I hit enter there. And also because I'm probably going to want to go back and forth, and I don't really know what 2 pi over 3 is in terms of radians, the decimal form. I'm going to switch this to degrees. So I'm going to look at that. The next thing I'm going to look at is I'm going to look at my format here, and I'm going to change from a rectangular form to a polar form, and I'm going to keep my axes on, and I'm even going to put some labels on too, because that's going to help me graph as well. So now when I go to y equals, I'm now going to have, oh, there it is. I'm now going to have a value of r equaling to something. So now, instead of me trying to figure out how would I even solve for y, I don't even know. But now I can just plug in 1 minus cosine of theta, and I get a really pretty picture. I'm going to get a really pretty picture. I hope you guys can see this. Let's hope, maybe I might have to zoom. Let me zoom in on this. So let me zoom standard here. There we go. So I get this pretty petal. So I'm going to zoom in a little bit just so we can see it better. And I get this nice little petal. It looks like a nice leaf maybe an acorn, and that's going to be 1 minus cosine of theta, or x to the fourth plus y to the fourth plus 2x squared y squared plus 2x cubed plus 2xy squared minus y squared equals to 0. And you can even do the same thing as if you were in the Cartesian form. Let's say we want to figure out what our value of r is when theta is, I don't know, we'll say 90 degrees. 90 degrees. We see our value of r is equal to 1. Let's say I want to see what happens when theta is 120 degrees. And I hit enter and I get a value of 1.5. So I recognize that there's these little circles that are continuing out. So we're going at 1.5. Let's say what happens if I'm at 360 degrees. Notice here I'm back at the origin. Let's say I look for 380 and see what happens here. It says, uh-oh, something's not right here. Let's go to see what's wrong. It says that I've exceeded that 2 pi interval. So then I could go up to my table set and I recognize that this looks pretty good. If I look at my my table here, I realize that my theta max is 360. Let's say I want to increase this to 720. And now when I hit enter, it's going to graph this once, and then we're actually just not going to see it. It's actually tracing that graph another time. So now if I were to type in trace 380 degrees, which is above 360, I would get a value. So you have to work with this. I'm going to post a couple videos. I don't use a lot of the calculator because I like to do things more traditionally, but it's a great tool and a resource to help you check your work. So keeping that in mind, let's go ahead and do some conversions. Let's do some conversions. Another sort of exciting. So I know before I talked about the generic circle that was centered at the origin, but let's think about how I would take a circle that was not centered at the origin. So x squared plus, let's look at y minus 3 squared and let this equal to a value of 9. So hopefully we recognize this is going to be a circle that is shifted up 3 units, so its radius is at 0, 3. I'll even do this out for us. So our radius is going to be here at 0, 3, and we're going to have the center is going to be at 0, 3, and the radius is going to be a value of 3. So it's going to look something like this. Actually worked out pretty well. So how do we convert this to a polar form? That's a great question. So remember, we know that x by definition is going to be equal to r times cosine of theta, and y is equal to r times sine of theta. So we know that that is going to be consistent, and then we know x squared plus y squared is equal to r. You can tackle these a couple different ways. It really depends on what makes you feel good. Sometimes I like to isolate x squared plus y squared equals to r squared. I like to do that. So I'm gonna do this actually first. This actually works well for me. So I have x squared. I'm gonna expand out y minus 3. So hopefully we all recognize that y minus 3 expanded through FOIL is gonna be y squared minus 6y plus 9. So here we're gonna have y squared plus, minus 6y plus 9, and this still equals to 9. I now recognize that x squared plus y squared equals to r squared. R squared minus 6y. If I subtract 9 on both sides, they go away, and I get this equal to 0. But we know y is equal to r sine theta, so we have r squared minus 6 times r sine of theta equals to 0. Okay, I'm feeling pretty good about this so far. So we can factor out r, so we're going to have r times r minus 6 sine of theta equaling to 0. So this implies that r equals to 0, or r minus 6 sine of theta equals to 0. Okay, I feel pretty good so far. Or r, just by adding, I could add, I'll show us, add 6 sine of theta on both sides. So r equals to 6 sine of theta. So here, if I were to graph this, and maybe we can go ahead and try it, we should get that circle opened up of radius 3. So let's go ahead and try that on our graphing calculator. We're doing some basic intro to graphing polar equations. R times sine theta, and this is equal to, oops, I might have to expand this out a little bit. I'm going to zoom standard. Oh, I still have it going 2 revolutions. So I'm going to zoom standard. And notice here I get that nice beautiful circle of radius 3 that's shifted up 3 units. So that's the neat part about converting, is this allows your calculator to do things that you in the past were told that you could not do. So, before, if we want to do this, we would have to solve for y. We would have to grab the positive portion of it, the negative portion of it. It would have been really cumbersome and not always the most easy to do. So, let's go ahead and try. Let's go ahead and try another conversion. So let's try some more conversions. I love conversions. So let's go ahead, and maybe if you want to try some out, you can pause these videos and see if you can get a solution. So we want to replace the polar equation. We basically want to convert this to a Cartesian equation. So we'll say convert to Cartesian. So how do we convert this to Cartesian? Remember, as we go through, that x is equal to r times cosine of theta, y is equal to r times sine of theta, x squared plus y squared is equal to r squared, and that tangent of theta is equal to y over x. So I tend to write these out just to make sure I remember them, because I know my memory is a little slipshod. This right here, r cosine of theta, this is x equaling to -4. So this is just a vertical line, x equals to -4. Let's go ahead and take out that calculator and see what happens. So where's my calculator? So let's go ahead and see what happens if I try to graph this. So before, there was no way for me to graph x equals to -4, but how could I graph this? Maybe I could graph this. I'll graph this by solving for r. Oops, I have to solve for r. So I'm just going to divide cosine of theta on both sides. So r is equal to -4 all over cosine of theta. So let's try this graphing calculator. So I'm going to have -4 divided by cosine of theta. And now when I graph this, I get a vertical line, and it is perfect. I've been able to figure out how to finally graph that vertical line that we were never able to graph prior to. I find that very exciting, very triumphant. So so that's just me. So yeah, good. I think that's pretty awesome. So let's go ahead and try another conversion. Let's try another conversion. So let's try another conversion. So this is going to be another conversion to Cartesian. Let's say we have r equals to 4 times 2 cosine theta minus sine of theta. So if you want to hit pause and see how this works out for you, you're more than welcome to do it. First thing I'm going to do here is I'm going to cross multiply, because I do not like denominators. I know before, if we were working in algebra, for example, we might have to say there might be some restrictions in our denominator that this does not work, that this does not work if theta equals to some value. For right now, we do not have to worry about that. And in calculus 2, you won't have calculus 2, you should not have to worry about that. So we know that we're going to have r times 2 cosine theta minus sine of theta equals to a value of 4. So now I'm just going to distribute that r. So I'm going to have 2r cosine theta minus r sine theta equals to 4. So remember that x equals to r cosine theta, y equals to r times sine of theta. Hopefully we see that we have r cosine theta here, r cosine theta here. So this will simplify to 2x minus, this is r sine theta. R sine theta equals to y, so 2x minus y is equal to 4. This is actually representation of a line. This is all this is a line. And so this would actually be the line of y equals to 2x minus 4. So this is a line of slope 2 and an x-intercept of 0, -4. I would never ask, even I don't recognize how to get that. I don't work enough with polar equations to automatically recognize that that's going to be a line with a slope of 2 and a y-intercept of -4. So sometimes it's not necessarily easier to use polar coordinates and polar graphs, but in some circumstances, as we saw before, it is.